So if you'll notice in the program, I had the talk listed as Metrology for Big Data, so I was thinking big. I figured here, on my slide for the title, I would add the Unstructured Big Data. I didn't put that in the title for the program because, in fact, unstructured usually insults lots of people, right? It's the shorthand that computer scientists used to mean data that was structured for human consumption, right? So it's not computer structured, but of course, data that is not computer structured does have structure of its own. The problem that I'm interested in, the overarching problem is providing people access to data that has not been explicitly structured for machine access. And the types of tasks that are involved in that and the type of data that is involved in that is big, using the traditional big data metrics in all the dimensions, right? There's lots of volume. Think of the World Wide Web scale for web search engines. But even if it's not at web scale, it's still generally too large for humans to process unaided. And a classic example of that, which has reached lots of, currently a big problem in the legal field is e-discovery, right? So now you have the enterprise, you've got your own devices, right? You have your iPads and you have your telephones and you have your email and you have your social messages. And all of that is now discoverable for lawsuits. How are you going to find all that information? There's also the problem of variety, right? Depending upon what task you're interested in, there are different media types, there are different genres, there's different languages, human languages, there's all sorts of different things which you might be wanting to search over. And there's the velocity dimension. Again, depending upon your task that you're interested in doing, there's the entire range of velocity, right? From basically static, think case law doesn't really change all that much, to the ephemeral, right? Tweets. You're gonna search over tweets, you better do it quickly or else they're not gonna be around for that long, right? So this whole problem that I'm interested in is content-based search. And there's lots of direct applications of that. You know them already. These days when I tell people that I'm an information retrieval researcher, all I have to do is say the algorithms behind things like Google, right? And people get what it is that I try and do. But there's also embedded applications, and actually some of these applications have already been talked about today. In the last talk before the break was actually a particularly nice lead-in to this talk, because what I'm really interested in, what my particular research is focused on, is how do you make quantified statements about how good your search algorithms are or your particular task that you're doing for this content-based access. I'm from NIST, as Henry said. NIST is the National Institute of Standards and Technology, and in its DNA is measuring, right? So the physicists of you out there will know NIST by its physics works, right? It's got a couple Nobel Prizes, mostly for atomic clocks, right? So it measures time. But NIST has lots of other laboratories as well. But the general basic common theme along all this is that NIST measures. And my role at NIST has been to try and measure particularly search engine capabilities, but also more generally, other natural language processing and content-based access tasks. The problem with trying to decide whether or not a search result is a good result is that searching is not in and of itself a final product, right? People almost never, unless you're a search geek, almost never just search for the sake of searching, right? That's searching for the end result of some other task that you are interested in accomplishing. And so therefore, what makes a quality search result depends upon all sorts of things. One is the goals of the searcher, the background of that searcher, The thing being searched, right? Sometimes really stupid search techniques will work fine if the thing is easy to find in that corpus. The other problem is that different humans will have different ideas about what is a good search result. You and I could be searching for the same thing and using the same query, and we will have different opinions about whether or not the results that came back from a particular search engine were good or not. So the thing that we have to keep in mind here is that there is no single truth, right? So now we're trying to measure something in which we don't even have a single, in which nobody agrees that there is one gold standard. The major paradigm that's used for, in particular for search engine evaluation was actually started in 1963 by a series of tests known as the Cranfield 2 experiments. And the Cranfield 2 experiments were not run actually as a way of being the founding for information retrieval evaluation, but that's what they turned out into be. And what the Cranfield test did was introduce this idea of a test collection. And a test collection in information retrieval is just a fixed document set, a set of queries, and then judgments about whether or not this particular document should have been retrieved for that particular query. And on the basis of those judgments, you can compute evaluation measures, the most common of which you've already heard mentioned today as well, are recall and precision. Cranfield makes a bunch of assumptions, and most of those assumptions are in fact not true, but they're good enough, and that's the real point. Because the rationale behind the Cranfield model is that this abstract task which is defined, which is just ranking a set of documents for this query, is necessary, but is not sufficient for any particular user task, right? Which means, in other words, if you can't at least rank the documents well, you aren't going to be able to do the other user tasks. But you won't necessarily be able to do the other user tasks even if you can rank well. And of course, since it is an abstraction, we gain power. That's why we abstract. We gain power in the experiments, but we lose the amount of realism that's not captured by the abstraction. So here's this whole complex search task of why people are searching and everything is completely ignored. It's all abstracted into this one graph, which is you're going to try and measure the difference between how well a perfect retrieval system would have ranked and what the actual retrieval system ranked for a particular query where, I don't have a pointer, I'll just point over here. You're trying to minimize this distance. This is what the retrieval system actually retrieved. This is what it should have retrieved, and you're trying to minimize that distance. Right? That's in search information retrieval captured in a single graph. Right? So, as I said, this started in 1963, was that the first test collection was introduced. In 1992, the whole idea of whether test collections were useful or practical or a whole bunch of other ols was in real doubt. Main researchers in the field decided that it was no longer a viable way of doing research because nobody was using the same collections, nobody was learning from other people's work because they couldn't. The measures that were being used were incomparable and the test collections were incomparable. So in 1992, NIST was asked by DARPA, it was part of a DARPA project, to create a large test collection to help in evaluating the DARPA performers' retrieval. And NIST countered, this was not me at the time, it was Donna Harmon, countered that instead of just building one large collection and letting it go at that instead we would build a collection, but we would also have a meeting, a workshop that would examine the whole issues surrounding how do you do information retrieval evaluation in the large. Now, in 1992, the large for research systems, the first TREC collections were 2 gigabytes of text. Today, that's a laughably small amount, but at the time, in 1992, 2 gigabytes of text was humongous, right? None of the research systems could handle it. There were DARPA grants explicitly for people to get disks to hold that amount of text. So Things have clearly changed since then, but the main ideas for Trek have remained the same, which is to form realistic test collections, to create uniform and appropriate scoring mechanisms, and to have this forum for the exchange of research methodology. Trek has been run annually since 1992. More than 300 teams have participated in some Trek. And there's been hundreds of research papers published in the proceedings, which are publicly available. And there have been, probably the most important part here, we have built dozens of test collections. And the two the previous talks this morning talked about the Reuters collection. That is a Trek collection. Well, it came through Trek from Reuters. Here's just an image. You probably can't see a lot of the detail here in the back, but this is just an idea to give you. These are the tracks that have been run in Trek. Here's each of the years along the bottom, the track name along the right-hand side, and sort of a gloss of what we were trying to explore in that particular test collection on the left. And while the Trek has in its name the Text Retrieval Conference, we actually have branched out from some text. In particular, we've done digital video. That's now its own evaluation conference called Trek Vid, because text and video are actually quite different. That's probably not surprising to you, but it's true. We've also done different tasks than just document retrieval. We've done question answering. We've done some speech retrieval, which is more of a search task, but now it's over speech documents instead of text documents. That's probably enough for that slide. In this 20-plus years now that we've been running Trek and these community evaluations, we've learned a fair bit about what community evaluations can do for a field. And these are the main things. It improves the state of the art. Trek has documented improvements in the basic search task of at least doubling, and that was actually in the first 8 years. We form or solidify, these community evaluations form or at least solidifies a research community. And it does that largely by, the resources such as the test collections that it builds, but also because it's the place where you establish the research methodology. How is it that you do research in this particular field? It facilitates technology transfer. I will ride on IBM's coattails here and say that their initial work on question answering that led to the Watson Jeopardy playing computer was originally done in the QA track in Trek. And it also amortizes the cost of infrastructure. If everybody out there has to go build their own test collection, then you're wasting lots of time on people building test collections, whereas if you can build it once and then have it shared, not only are you amortizing the costs, but you're also getting the benefits of the cross-community evaluation on actually the same collection. So what's NIST role in all this? Well, NIST organizes Trek, but the reason why it is at NIST is because we are a technology-neutral site with the technical understanding. The technology neutral here means that we don't have a horse in the game, right? We don't care whether you use deep learning or bag of words or anything else you want to throw at me, right? The idea here is we want to see at the end user task, how well does it work? We also keep the artifacts, and I would have said that we were the keeper of the artifacts up until, of course, the past 2 weeks. The Trek website was not available, but when the government is open, the Trek website has all the public proceedings, it has all the data sets, and it has an archive of past results. Now, how does Trek and Cranfield intersect? Well, obviously, Trek, first of all, is based on this Cranfield tradition in that what we're building is test collections. However, Trek and the research that has happened through Trek, and particularly this archive of past results, has allowed us to extend and validate Cranfield in a way that it never had before and was never able to be done before Trek. We've extended it by adding it to new genres and new tasks. We've been able to show empirically what the effect of particular implementation decisions on how you build your test collection, what effects those have what conclusions you can draw at the end. We've developed, and this is mostly work that's done specifically at NIST, we've developed reliability and sensitivity tests about how reliable are the results that you get from a test collection and how fine of distinctions between systems can you make. And we've, not just NIST, but the TREC community as a whole, has also developed new evaluation measures. The problem with this whole idea of trying to measure retrieval performance and using Cranfield is when Cyril Cleverton, who was at the Cranfield Aeronautics, which is why it's called Cranfield, created his experiment that started this whole thing. He was explicitly trying to remove the user from his experiments, right? He was trying to reduce his variability by removing the user. So in Cranfield, the user is just whatever topic, which is Trekkies for query, so whatever the information that is being searched for, and the relevance judgments, which is the statement of, yes, this document is relevant, and that one is not. That's the only place within Cranfield that a user appears. And despite this stark abstraction, the user effect is still the greatest effect on the evaluation quality of a search. In TREC 3, using TREC 3 results, there was a paper that showed that the topic effect and the system were both statistically important effects, that they did have interactions, but the part that's most unfortunate for me as a measurer is that the topic effect is much greater than the system effect, right? What this means is that what is being asked for, the difference that causes on the evaluation results is generally much bigger than which system you use to search. And if you're trying to measure the system performance, that's unfortunate. Here's a graph which I frequently show, and depending upon whether you are an information retrieval researcher or from some other discipline, it's either old hat to you or it shocks you completely. This is a recall precision graph, interpolated recall and precision. Basically, all you need to know that is if a perfect system would be in the 1-1 point, but this is sort of typical behavior. That big heavy line is the average, and that's what everybody always uses, is averages over topics. But that average over topics is hiding a lot of variability. This is the other lines are the performance of individual topics that go into that average. So the top line, sort of the dark purple at the top, that's actually a topic that this particular system did very well on. But you can see sort of there's a line there that sort of basically stays at 0. That's a topic the system did very poor on. And we're trying to gauge how well a system does from averages when the averages are hiding that amount of variability. So this fact that this user effect is the biggest effect, the implications for that for the evaluation is that we're trying to detect a relatively small difference. So we need both a sensitive and a stable protocol to do that evaluation. And both the sensitivity and the stability depend upon the number of topics, at least in the way that things are currently evaluated. There's a strong negative correlation between variability and experimental power, right? The more variable things are, the less power your experiment has. But there's also a strong positive correlation between power and cost. The more powerful you want your experiment to be, the more expensive it is. Cranfield, probably by luck, when Cleverton first developed it, is in fact carefully calibrated in a particular place where that power exists and the costs aren't too bad. But any additions to the Cranfield model increases the variability and therefore increases the costs and lowers the power. So Cranfield has been successful because it is at this carefully level of abstraction. But future IR test collections, and actually current IR test collections, need different abstractions, and that is because, first of all, size matters. Remember I said that Trek started, it was 2 gigabytes of text, and that was just unheard of large. Because of that unheard of large, there's all sorts of things that the information retrieval community learned on those 2 gigabytes that actually explicitly contradicted things that had been learned on the smaller test collections that came before that. And the biggest thing of that is, and while it wasn't put in these terms than that, but it was basically machine learning works, right? Relevance feedback had been, is an information retrieval type of machine learning. It had been tried in all sorts of different collections basically from the early 70s. And it wasn't really until you got the large enough collections that the power of that actually became clear. However, the collections are currently built by sampling from the document set. Not uniformly by any means, but we still sample. And at some point, those samples still have a dependency on the size of your document set. And at some point, those document sets are so large that your sample, no matter how you sample, for it to be operationally feasible, and basically what I mean from this is that sample we put in front of humans, and those humans sit there and judge it. And you can only do that for so long, right? And at some point, your collection is large enough that that just plain doesn't work. And we're pretty much at that point now, frankly, and I don't actually have a replacement yet. Currently, what we've been doing, I guess for the last 7 years, say, is we've been looking at ways of doing sampling smarter and smarter, but we're really reaching that limit. There's another problem here, that a lot of the benefit from Trek came from this idea of having everybody working on a common data set. And we have also reached tasks here now where having a common data set just isn't tenable. And the prime example, and the one that's in most of my mind now because I'm currently trying to deal with it, is electronic health records. We'd really like to be able to have search over electronic health records, but try getting a set of electronic health records which you can distribute worldwide. It isn't happening. So the current research is on how can we attack those types of problems. And I just want to put a plug in here as my last slide. There is a new effort being started at Trek called the NIST Data Science, not at Trek, sorry, at NIST, at the NIST Data Science Symposium. It will be held this year on November 18th and 19th at NIST. The idea here is to define a metrology for data science more broadly than just information retrieval research. It's free, but you have to register by November 11th. There's a URL for it. And thank you. Yes.
Some of your problems with distribution and scale can be addressed by switching from a paradigm where you give out data sets and evaluate results to a paradigm where you give out login to a big Hadoop cluster.
So the question was, instead of distributing data, have people log into a sort of a common place. We were trying that for the first time in Trek 2013. There's the microblog track is search as a service, and then that's because largely we couldn't distribute a Twitter corpus that was large enough to be meaningful. And so the idea here was to have it in a common place. So yes, that is one. There are issues there. Actually, the spam track tried a similar sort of thing, where it had a jig, an evaluation jig, and you sent your results. You didn't actually get because that was another place where people don't want your email, don't want to give you your email to distribute across the world either. And so that email stayed behind at a common place, and you just submitted your results.